Sorry for the small delay. There has been a small glitch with the transport. Anyway, we're all back. So we have the pleasure to welcome Glenn Beng from the University of Innsbruck, who will continue the introduction of related to foundations of quantum computing. And after this course, there will be a welcome reception that is going to take place on the terrace where we had lunch. Okay.
Okay, so thank you very much. So as probably you know, I'm going to speak today about adiabatic quantum computation. So let me start by giving a few references on the topic. So just an overview is going to be this recent review by Albash and Lidar named adiabatic quantum computation. So this is a review of modern physics. So from 2018. So here you're going to find basically all the references you can about the topic, and you're going to find the latest results and the references to the latest result and latest theorems in this topic. And but this is not very self-contained. It's not an introduction. It's just a review. So if you want to read something which is self-contained, and I'm gonna recommend for you the lecture notes by Childs Andrew. And it's gonna be lecture notes on quantum algorithms. So here you have an introduction to the topic, which is self-contained, and if you are willing to read it in depth, there are also rigorous proofs about the statement that are mentioned. So till now, you have probably seen the gate model, right, for quantum computing. So in this model, essentially what happens is that the system undergoes a sequence of gates that form a circuit. So I'm going to go pretty fast on this because you've already seen it. And the final result is going to be measured, and you're going to get output. So in this kind of approach, you have what is would be a digital quantum computation model, because you're applying these digital gates, so these elements. While now I'm going to discuss adiabatic quantum computation. So And this model is quite different because instead of being digital, it's going to be analog. And the system is going to be evolved with a certain time-dependent Hamiltonian. And we are, yes, sorry, okay. Yes, maybe. Okay. You can still make measurements at the end, and you're going to always get an output. So here, the dynamics is governed by the Schrödinger equation, which is implemented by this time-dependent Hamiltonian. And the output, again, should be the solution of your computational problem. So why would we try to do this kind of approach, and why is it called adiabatic quantum computation? So the reason is that the goal, in the end, is to prepare the system in, let's say, C out is going to be ground state of H of the final time, which is the final Hamiltonian. So the output is we want the output to be more or less the ground state of a final Hamiltonian, and we want that the ground state of this final Hamiltonian would be encoding the problem. So the reason why we do this is because in physics, we more or less have techniques to prepare ground states of Hamiltonians. We have techniques to prepare ground states of Hamiltonians. And the idea is to apply these techniques in this case to come up with a new computational, with a new algorithm and model for computation. So now the question is, how can we prepare the ground state of a certain Hamiltonian given a certain time with a time evolution, with a Schrödinger evolution? And this can be done relying on the adiabatic theorem, which is the backbone of adiabatic quantum computation. So let me state it. So the adiabatic theorem, first of all, let's, before stating it, let's try to discuss what are the ingredients. So we have an Hamiltonian, h of t, which is time dependent. So this Hamiltonian, being time dependent, is going to have a spectrum, which is also time dependent. So we can solve the time independent Schrödinger equation, the eigenvalue problem for each independent time. So we will then get such a spectrum that's going to be given by, let's say, this, the energies and the eigenvectors as a function of time, Sorry, again bigger. Sorry. Oh, this is the right size. Translate. Okay, let me. Hopefully. So, okay, so from here, as we said, so the Hamiltonian is going to have eigenstate and eigenvalues which depend on time and satisfy the following equation. So if I apply the Hamiltonian to an eigenstate, it should just get be multiplied by the eigenvalue. Okay, so we have this, and if we look at the Hamiltonian at the spectrum of the Hamiltonian as a function of time, and we're going to have energy levels, and we diagonalize the Hamiltonian and look at the spectrum at each time. So would have the first energy level, which is going to do something like this, which will depend on the time. Would have, let's call it, I'll put it on top because this is a function. And so this is an A0. It's not an important, because it's small. It's not really important. And then you're going to have other levels. For, let's say, this is going to be for the state 0 of t. This is going to be for the state 1 of t. And et cetera, for all the levels of the Hamiltonians. Okay? And we make the hypothesis that these levels do not cross. In particular, that the ground state, so A0, it's always different, or in this case, since it's the ground state, A0, AM of t is going to be always greater than A0 of t, meaning that this cannot happen. Okay, so this is not contemplated within the theorem as I will be stating it now. And having this hypothesis, we can now start stating what the theorem says. The theorem says that if we start from an initial state, say of 0, which is the ground state at time 0. And then we let the system evolve with the Schrödinger equation. So okay. In the end, we are going to get that the state of the system at time t, psi of t, is going to be, let's say, approximately proportional to the ground state at time t. Okay, so this is saying that And for this condition to hold, we have to have a sufficiently slow evolution. So I'll write it here because it's quite important. So if the Hamiltonian is changing sufficiently slowly, what will happen is that the state would always remain in the instantaneous ground state, the evolved state. And thus, I can use this idea to prepare the ground state of a final Hamiltonian, starting from the ground state of an initial Hamiltonian. So before describing in detail how we can use this in quantum computing, I want to spend a few seconds, like a few minutes, discussing the proof and the bounds that are related to this theorem. So, okay, I'll just delete this. So this is, to make this statement, to give a quantitative statement, we need to be a bit more precise than what I've said here. So we are going to consider that the Hamiltonian h of t is, let's say, it's going to be equal to h of s with s equal t over the total time. So we can take, if we want to be more precise, let's say we are evolving with h prime of t, which is equal to this function. And now, in this case, we can rewrite the Schrödinger equation as a function using the variable s. And we are going to get that we're going to have a psi of s. And we're going to have that for this psi of s, the derivative in s is going to be equal to minus t psi of s, and of course the h of s. Sorry. Okay, so in this case, by doing this change of variables, we get a time here. And this change of variable is quite relevant because this parameter allows us to slow down the evolution. So the Hamiltonian, for example, we can take as final point h of s0, initial point, going to h of s equal 1. Okay? And this, in terms of the time, is going to happen within a time from 0 to capital T. So by sending capital T to infinity, I make this dynamic slower and slower because it takes more time to reach the final Hamiltonian. So I have to be doing this change slower. Okay, so this is the setting, and with this setting, it's possible to start attempting to prove the theorem. So I'm going to give not a rigorous proof of the theorem, which you can find in the lecture notes from Childs, because this is maybe not the right place to prove the whole theorem. But I just want to give some idea on how the theorem works, on how to prove the theorem, and what comes out from the theorem. Because other than knowing that if we send t to infinity, the dynamics is going to be adiabatic, so it's going to stay in the ground state, would like to know how large t has to be for this kind of statement to hold. Okay, so I'm going here. So to make the proof, the first part of the proof is going to be to find an exact adiabatic evolution. So we say that this Hamiltonian, when this condition hold, will be approximately in the ground state, but we want to find an Hamiltonian which we want to define an Hamiltonian, an alternative Hamiltonian, HA of S which is going to be T H of S plus I P dot P. So here P is the projector over the instantaneous eigenstate. So if we want to be precise here, we should put S, but I will drop the S where they are like, so I may drop the S where it's implicit. That all these things except T are going to be S dependent. So the first statement is that this is going to be implement an exact adiabatic dynamics. So if I evolve with this Hamiltonian, I'm going to have that the Schrödinger equation can be satisfied. So let's say Schrödinger equation for A. Oh, sorry. Okay, so we said that if this, so the main thing here is that what does it mean that this implements the exact adiabatic evolution? It means that if I take psi A of S, which satisfies the Schrödinger equation with HA, okay? So if I consider this Schrödinger equation, then with initial condition that I'm starting from the ground state, then I'll have that the solution is psi A of S equal to a coefficient times the instantaneous eigenstate. So wait, let's put S here because we want to keep everything in terms of S. So this is going to be a solution of this equation with some appropriate C0, okay? And this means that the first step is defining an Hamiltonian which does the job exactly, which is implementing an exact adiabatic solution. The next thing that you would have to do for the proof, yes. So the next thing that you'd have to do for the proof is showing that if I take the evolution operator, let's say, I would say UA and U are close. So here, the evolution operator UA is the evolution operator induced by this Hamiltonian, by the exact adiabatic Hamiltonian. So it's going to be satisfying the equation HA UA. And the U is going to be the adiabatic, the evolution implemented by our original Hamiltonian. And this is going to be satisfying the HU. So again, both of these are, here the derivative, of course. Again, both of these are function of S. Okay, and as I said, everything except T is basically a function of S. So in this case, these two, I know the differential equation satisfied by these two operators, by these two evolution operators. And the idea is that I want to show from this that UA minus U this should be small. For T that goes to infinity. So after defining the evolution, the main point, as we said, we have defined the exact adiabatic evolution, and then the idea is to show that the exact adiabatic evolution is actually close to the evolution operator induced by the time-dependent Hamiltonian, the original one, when the process is slow enough, so when T is going to infinity. And finally, again, the third step here, which I'll write here. So the third step is going to be to put some conditions. So it's going to be to say how large T should be. Okay, so these are the steps that lead to the proof. I've not proved none of them at the moment, but I want to simply start by proving the first one at least, because it will it will give us the evolution, the state which is, and the phases which are actually implemented by this slow evolution in the limit of t that goes to infinity. So again, let me start by, so as we said, this here. So I'll look at the first step. And we say that this is going to be our h of s. Okay? And the idea in this first step is to show that, as we said, that the Schrödinger dynamic, this satisfies the Schrödinger equation. So let's write that explicitly. So if this is this will satisfy the Schrödinger equation, if we're going to have that the derivative of, let me just write here that this is the wave function, okay, the state, and we're going to have that the derivative of the state should be plus the part due to the Hamiltonian okay, let's just keep the s out for consistency. So this should be equal to 0 if we want that the Schrödinger equation is satisfied, because I just brought everything on one side in the Schrödinger equation. Okay? So we can start writing this and see what comes out. So the first part is going to be here. So since there are going to be a few derivatives, I'm going to use the notation x dot equal ds of x. Okay, and this is going to be the first part. And the second part, we have to put in the Hamiltonian. So we're going to use the eigenvalue equation. So since A0 is an eigenvalue of an eigenvector of HS, this is going to be E0 times E0, and then we're going to have plus this term. So so plus, and we're going to have E times E P dot P. Okay, and this still applied to E0. So let's put here the coefficient because of linearity. The C0 goes out from this application. So yeah, Okay, so to be consistent, actually, if we want to keep the h bar, sorry, here, I forgot an h bar. Okay, so here we're going to have a 1 over h bar, and we're going to have an h bar. Okay. So this equation, in this equation, actually, what we would like to simplify, to resolve, like to simplify, is this object. So let's write what this object is. Yeah. So we are going to have P dot P applied to E0, which is going to be I just recall 1 second that P is E0, E0, okay? And this here is gonna give it's 0 dot, comma, sorry, I'll write this here. Okay. And this is going to be is 0 dot is 0. Okay. And is 0. Okay, so now we're going to insert this in the equation, but I'm not going to do the computation bit by bit. I'm just going to give you the result for this one. And what you're going to get is that you're going to have that when you insert this inside here, you're going to have that the Schrödinger equation, which should be 0, is going to be actually C dot is 0 plus, so plus E H bar is 0, and this is going to be plus. Let me just get you the right sign for the last term. And you're going to have minus I is 0 dot. Okay. And this is going to multiply is 0. So what happens is that the Schrödinger, all the terms in the in the equation vanish except those that multiply directly the single eigenstate E0, and then we have an equation with just coefficient on a single vector. And this equation, here, of course, there is a C0 missing. And this equation has a solution, which is going to be that the C of T, or of S in this case, is going to be an exponential of a dynamical phase and a geometric phase. Okay, times the C at 1, and we will, because of the initial condition C0 at 1, this is simply going to be the value of C. And here the phases are given by are the integrals of these objects that appear here. And gamma is going to be the integral of I0 is 0 dot. Okay, so what would happen is that the state would approximately evolve, acquiring, let's say, these two different phases. One is simply what you would expect in a usual Hamiltonian, which is in a usual Hamiltonian, you would acquire a phase proportional to the energy times the time, if the Hamiltonian is time independent. In this case, you have to, the E depends on the time, so you'd have to integrate this. And in the second term is due to it's a geometrical phase, which plays an important role, for example, when you want to consider cycles which return at the initial point. But in this case, what we are mainly interested is in the dynamical phase, and I just want to mention that if you proceed in doing proving the theorem, you'd find that the oscillations that are induced by the dynamical phase are what essentially allow you to prove the theorem, because you're going to have that the eigenstate is that the state is having that the state is having phases which are high, and you're going to have that when you compute integrals, these phases are going to appear in the exponential, and you're going to have to integrate by parts to obtain a bound for the error. So let me, I'll skip this part because it's quite technical, and I'm just going to give you the result for the bound. So okay? So if you finally attempt to estimate how far it's your state from, so how far it's your evolution from the exact adiabatic evolution, you're going to have that this, you're going to be able to write this equation. This is going to be, let's say, you're going to have an error which is smaller or equal than time some constant. So you're going to have an error which is, okay, here you have a total time. So you're going to have like that the error times the total time. It's let's say it's smaller than the norm of the derivative of the Hamiltonian divided by the gap squared, where the gap squared is the gap is the, let's say, is going to be the difference. Let me write it here and I'll then draw it. It's going to be 1 of t minus E0 of t. And you're going to have that, as we said, you're going to have these two objects. And we are considering this difference between the E0 state and the E1 state. And here, you would have to take of this quantity is defined for some value of S, and you'll have to take the maximum. So actually, let me write it explicitly, that you have to take the maximum. Okay. So this is what the theorem states, that the error that we define, and it's telling us how close the state of the evolved state is to the state implemented by the exact adiabatic Hamiltonian. And this error, if I call it epsilon, so if I call the error epsilon, let's say here, I'm going to have that the time needed to achieve an error epsilon is going to be 1 over epsilon times a constant times the maximum over S of H dot square of S. So this is telling us that, again, as I said, I'm calling epsilon the error. Okay? So this is telling us that if we want to keep a certain fixed error, so we want the final, for example, the final state to be pretty close up to epsilon to the ground state of the final Hamiltonian, we are going to have to increase the time, because when we reduce epsilon, the time is going to increase. But on the other hand, it's also telling us that to achieve, when we have a fixed epsilon, we can achieve a sufficiently good performance if we choose the time large enough. And what is the physical, what are the physical quantities that are defining how large this time has to be? These physical quantities are the derivative of the Hamiltonian and the gap. So let's say if, for example, the derivative for some reason is constant, we are going to have that the time is going to be scaling with the inverse of the square of the gap, the time to have a certain error epsilon. So this is the adiabatic approximation because it tells this equation tells us this equation tells us how long we need, how much time we need to achieve a certain precision. And now I want to describe how this is used in, briefly describe how this is used in adiabatic quantum computation. Yep, so I'm going to use the last few seconds. So for this, I'm going to just finally describe the algorithm. And like tomorrow, I will show practical examples. But today is just about understanding what the algorithm is and what are the theoretical foundation of the algorithm. So if we start from a certain Hamiltonian, let's say h of I, an initial Hamiltonian, and we want to end in a final Hamiltonian, which encodes the solution of a problem. So to do this, we would have to restrict. It's easier actually to restrict ourselves to some combinatorial optimization problem. So we consider the problem of minimizing a certain function, let's say h, defined on binary to R, okay? So we consider this problem. Mean of h of z. So this is an optimization problem because we are given a classical function and we want to find the zeta that minimizes the function. So actually many problems can be written in this kind of form, and also quite complicated problems which are NP hard. And for example, like the satisfiability problems, the traveling salesman problems, and I will discuss some of them tomorrow. And also the Grover problem that you already saw can also be written in this in this kind of shape. So if you have a problem which can be recast in the finding the minimum of this function, finding the minimum of this function can be again recast in the equation of finding the ground set of a certain Hamiltonian. So we consider this Hamiltonian, which is going to be the sum over all the possible strings z of, and we define the Hamiltonian, we define a diagonal Hamiltonian. So the elements of the diagonal are given exactly by h, and the eigenvectors are exactly this. The eigenvectors are exactly the computational basis. So again, Z is going to be a string, as we said, with each of these values can be 0 or 1. So this can be seen as a state defined on a set of n qubits. So we have that this Hamiltonian n lives in the space of n qubits, and the ground state of the final Hamiltonian, since the Hamiltonian is diagonal and we already know the energies, is going to be the state which has the minimal energy. So in this case, it's going to be the state which has the minimal h of z. So it's also going to be the state which minimizes, it's also going to be the state z which minimizes our function. So the ground state of this problem is going to be let's say E0 of t equal capital T at the end of the evolution is going to be the zeta bar star, so that zeta bar star is the minimum of our initial problem. And in this case, we can use the adiabatic theorem to generate an Hamiltonian that produces the ground state of this problem. And to do this, we consider the following Hamiltonian. So the interpolating Hamiltonian, H of S, which is going to be, let's say, let me give you a simple form, but this can be changed. So this is going to be S times H final plus 1 minus S times H initial. And I recall that S is T over T. So in this case, I'm giving you, this would be a particular case where I've chosen a linear schedule. As we'll see, this may not be necessarily the best one, but at time 0, the Hamiltonian is Hi. So it's going to be H of S equals 0 is going to be Hi, and H of S equal 1 is going to be HF. Okay? And if I am able to prepare the system in the initial state, which is one of the requirements for the adiabatic theorem, so that I must be able to prepare this initial state, which is the ground state of the initial Hamiltonian, then the adiabatic theorem assures us that this evolving with this Hamiltonian is going to generate the solution we are looking for. Okay, so this is essentially how things are going to work. And for the time I need, because we said that this I need a certain amount of time to do this, and the time I need is going to be dictated by the derivatives of that Hamiltonian and its minimal gap. So I can get the runtime of the algorithm up with a certain precision. So this is a runtime at fixed precision by computing this object. So the analysis for when running this kind of algorithm for a certain problem is going to be write an Hamiltonian, which interpolates between an initial one and a final one. The final one should solve your problem of interest, and the initial one should have a ground state which is sufficiently easy to prepare, so we should be able to do this ground state preparation. And after the evolution, if the time is longer than a running time, which is depends inversely with the gap squared of the Hamiltonian along the evolution path, the system is going to return the ground state of the final Hamiltonian, which is also the solution of our initial problem. So this is just let's say, the theoretical side. So how the algorithm should work in theory. And tomorrow I will discuss explicit examples for the algorithm, and I'm going to show how it actually works in practice for some specific problems. Okay. Thank you. Yes? Yeah, so it's not so important. So in this case, the norm is 2 norm, but